The shape design of the hall is directly related to the time and space composition of reflected sound, and it should integrate acoustics and architecture to meet the requirements of acoustic design. The main design principles of the hall are as follows. The first, ensure that the direct sound can reach every listener. The second, ensure a good distribution of earlier reflected sound. The third, prevent echoes and other acoustic defects. The fourth, apply proper diffusion treatment. The fifth, make reasonable use of the stage reflector. Item 1 needs to prevent listeners at the front from obscuring the listeners at the back. Small halls can be equipped with a podium to raise the sound source, and large halls should gradually raise the ground from front to back. Since the wavelength of the sound wave is no longer than that of the height wave, the propagation requires the wave front to have a sufficient width, so the ground needs to be higher than the height required by the line of sight. Article 2, considering that reflected sounds with different delays have different effects on sound quality, the delay can be calculated by dividing the propagation path difference between the reflected sound and the direct sound by the speed of sound. Echoes may occur when the delay is greater than 50 milliseconds. At this time, the sound path difference between the reflected sound and the direct sound is greater than 17 meters. This formula can be used to determine whether an echo will occur. Small-scale halls generally do not need special treatment for body shape, and the delay of the first reflected sound at most receiving points can be controlled within 50 milliseconds, while large-scale halls need to meet this requirement through body shape design. Let's first look at the design of the flight shape. This figure shows the distribution of the first reflection sound from the set halls for 3 basic flight shape halls. Picture A is a rectangular, and the distribution of the first reflected sound is uniform. Picture B and C are fan-shaped. Picture B has a large depth and a small width than picture C. The uniformity of the distribution of the first reflected sound is better than that of picture C, and the central air of picture C lacks the first reflected sound. It shows that the distribution of reflected sound is related to the ratio of the depths and widths of the hall. The plane shapes represented by these pictures are more complicated than the previous picture, namely the width is larger than the depth, the width is similar to the depth, and the width is smaller than the depth. The 3 on the left reflected the distribution of the first reflected sound from the side walls, and the 3 on the right give the treatment measures and their effects. Picture A has a good site conditions and is often used in buildings with performance needs. However, most areas lack earlier reflection sound, and the first reflection sound from the rear wall has a long delay. The ceiling and the rear wall can be diffused, the sound absorption can be scattered on the rear wall, and the electric sound can be sublimated in the middle. The middle part of the picture B lacks earlier reflection sound, which is easy to produce echo. The 2 side walls close to the stage can be made into polyline shapes, and the rear wall can be diffused or added with balcony. The ceiling close to the stage can be used to provide the first reflected sound for the central area, and the side walls can be used to reflect or diffuse to the middle. Fig C is close to a rectangular, and the walls on both sides are close together, so it is easy to get the first lateral reflection sound, which is suitable for music performance. However, due to large depths, it is easy to form echoes and multiple echoes. The side walls can be appropriately undulated for large halls. The side walls near the stage are processed into a fold-like shape, reducing the opening engine so that the first reflected sound reaches the middle and the front of the hall. The main object of the section design is the ceiling, and the reflected sound from the ceiling has the most effective influence on the indoor sound quality. The principles of roof design are: first, the ceiling is designed as a folded surface or curved surface that generally rises from the upper edge of the proscenium, so that the first reflected sound generated by the ceiling at the front of the hall, that is, near the stage part, is evenly distributed in the auditorium, as shown in the upper and lower picture on the left zone. The second, the ceiling after the middle is designed as a diffusion surface that reflects toward the entire auditorium and side walls, as shown in the middle image on the left. Concave curved ceilings are prone to sound focusing and should be avoided. When it must be used, sound absorption can be done on the inner surface of the ceiling, or as shown in the figure on the right. A floating cloud, that is, a reflector, can be set under the ceiling. The upper left image compares the area of the vertical side wall and the inclined side wall that can provide the first sound reflection to the auditorium, and the first reflection surface is below the normal of the wall. It can be seen that the inward sloping side wall have a larger area. Therefore, it should be used when conditions permit. The vertical wedge-shaped undulations can be arranged on the vertical side walls when there are no conditions. The method in the picture below on the left is suitable for a wider hall. By raising the seats close to the side walls, the lower wall below the seats is used to provide the first sound reflection to the middle of the wall. Due to the poor acoustic conditions of the seats and the balcony, it is difficult for the reflected sound from the ceiling to reach here, and the reverberation time is shorter than other places. Therefore, the depth of the space below the balcony should not be too large, and the size requirements are as shown in the figure on the right. In addition, the ceiling and the balcony should be tilted backward as much as possible, so that the reflected sound falls on the seats and the balcony. The balustrade at the front of the balcony should be diffused, so that the reflection is directed towards the nearby auditorium, so as to avoid reflection back to the front of the hall. Acoustic designs mainly include echoes, multiple echoes, sound focusing, and sound shadowing. Echoes cannot be accurately predicted in the design stage, and the sound ring method is currently used to test and judge the possibility of the echoes. The method is to use the delay formula introduced above to check whether the sound path difference between the reflected sound and the direct sound is greater than 17 meters. That is, whether the delay is greater than 50 milliseconds. The position of sound source is set in various possible positions, and the situation of the speaker as the sound source should also be considered for the electroacoustic sound. The reception point should not only consider the auditorium, but also the stage. The above picture shows the most prone to echoes, namely the back wall, the ceiling near the back wall, the front of the ceilings at sector. Rear walls with concave curved surface should be avoided as much as possible due to the fact that acoustic focusing will enhance the intensity of echoes. The figure below shows the treatment method. You can diffuse and absorb sound on the rear wall, or adjust the inclination angle of the wall so that the reflected sound falls into the auditorium nearby. Multiple echoes are due to multiple repeated reflections between specific interfaces in the hall. In the auditorium-type hall, because the sound source is on the stage and the hall is full of auditoriums, this phenomenon is not easy to occur. On the other hand, the hall of gymnasium type, shown in the figure above, may have repeated reflections from the ceiling due to the sound source on the ground, so multiple echoes are easily formed. Several situations shown in the figure below are multiple echoes caused by improper sound absorption arrangement and plane shape design. Therefore, both plane design and sound absorption design need to pay attention to avoid echoes. Acoustic focusing is caused by a reflective ceiling or wall with a concave surface. The reflected sound is concentrated near the focal point, and the reflected sound at other locations is very small. Sound shadow refers to the area where the earlier reflected sound cannot reach due to the occlusion, and it is easy to form sound shadow and the balcony mentioned above. Both sound focusing and sound shadowing can make the sound field extremely uneven and must be prevented. The diffusion treatment adopts the method of undulating surface or staggered arrangement of sound absorption and reflection materials, and is generally arranged on various surfaces other than the first reflection surface, such as the middle and rear parts of the side wall and the ceiling and the rear wall. Diffusion processing is used to eliminate echoes and sound focusing, increase the uniformity of sound energy distribution, smooth and growth and delay of sound, and help avoid coloration. Acoustic coloration refers to the spectral change caused by the superposition of strong reflected sound and direct sound, resulting in temporal distortion. The diffusing effect of a contoured diffuser depends on the size of the diffuser and the wavelength of the sound waves. The size of the diffuser is comparable to the wavelength of the sound wave to have a diffusion effect. By designing diffusers of different sizes and shapes and arranging them irregularly, the diffusion effect can be achieved in a wider frequency band. The stage reflector is used to reflect the actor's sound energy to the auditorium, improve the sound energy density of the auditorium, and enhance the actor's self-hearing and metro hearing between the actor and the band and each part of the band. Stage reflector should be reflective over the full frequency band in a plate-like structure and lined with stamping material. You can go to school halls and gymnasiums to check whether they meet the sound quality design principles, see if there are acoustic defects, and try to give suggestions for improvement.